Okay, so we'll just wait for some time and get started for others to join in case. Okay. So you can hear me, right?
Yes, ma'am, I can hear you. Can you hear
Okay.
me?
Yes,
Yeah,
yes, yes. I can hear you. And
yeah,
the screen is visible and video and
yes, ma'am.
everything is fine, right? Yeah. I'm not
Yes.
able to see myself, so I'm just like I'm supposed to
No,
keep my video on, so I was just trying to see if you
no,
can.
no, it's visible. Thank you.
Okay. Yeah, thank you. So so I am Sauravi. I am PhD student here at IISc, and this is a part of PMRF TA-ship that we are trying to do. And today we'll be talking about electromagnetic theory. So to start with, when in the last class we had a brief, discussion about vector algebra, which is very fundamental in understanding uh, how this theory came. So we discussed about the basics of vector algebra, and from there we went to the introduction to electrostatics, where we spoke about Coulomb's law. Now today we'll take it up from there. So to start with, first we will look closely, a bit more closely into vector algebra and what this, we heard about or we discussed about divergence, curl, and gradients, right? So, what does these things physically mean? So, that's very important for us to understand because this entire idea of electromagnetic theory is very fundamentally dependent on this concept of field formulation. And so, how one characterizes a field is very important. Okay. So, we will look closely into what gradient means, what divergence means, or what curl means in using certain examples. And then we'll proceed forward towards towards electrostatics. But now by using the symmetry of the system, we'll see that we can simplify things. Like we might not have to do proper integrations all the time. Okay, we can just work out and make use of the symmetry. And there an important law comes up, which is the Gauss's law that we'll be discussing today. Okay, so understanding gradient divergence and curve. So to start with, just like we know what the del operator is. So if you have any doubt, you can uh, stop and ask. Okay. So we know what the del operator is, and this is how it looks like, right? So del x I cap plus del y j cap, del z k cap, and this is a vector. And then if you have a scalar field like phi of x, y, z, which is a function of its position, suppose. Now we can do a gradient of phi, which will be a vector. And what we discussed last time is that it gives the direction in which the phi has its maximum change. And now if you want to find the change in phi in a particular direction, you can take a dot product in that direction, right? So that was about gradient. Now about divergence, we saw that if you have a vector, then you can again use this operator on the vector. What you end up getting is a scalar quantity, okay? And that tells us how the field lines are, whether they are moving inwards from a point or coming to a point, how are they emanating from a point, okay? So that's about the divergence. And then we spoke about curl, which is like again using this operator on a vector, but doing this cross product, and this gives us a vector. Okay, so curl is a vector which tells about how the field lines are like whether the field lines are circular or not, whether there's a rotation in the field lines or not, right? Now, there were all these different formulas, and like some of them are very easy to remember, some of them are a bit uh, like not so trivial to remember, but you can try like solving questions and trying to remember them, especially like this number 6, number
Yes.
7, 8, or 12. Okay, these are important formulas.
Okay.
Now, let us look at this question and try to, go deeper into gradients first. So if we have a scalar like this, which is a function of x, y, and z, okay, and we want to find gradient of phi at a particular point, right? So we know the formula, we can do this, right? We end up getting a vector, and we can like put the x, y, z value. So this is a vector. Now, what is this vector telling us? It's a direction in which phi has its maximum change, right? But how does it look like? Okay. So, do you have anything to add? Like if you already have an idea about what this vector, physically looks like, you can like uh, unmute yourself and tell me, or else we'll try to look at it step by step.
Can we look at it step by step, actually?
Yeah. Okay. Sure. So
Hmm.
this is a vector,
Thank
right? Now, phi is a
you.
scalar quantity. So what one can try to first solve is this, and then the idea of what this gradient of phi is will be clearer. So this question
Okay.
says that can you show that gradient of phi is a vector which is perpendicular to the surface phi equal to some constant? Basically, what it is telling you is you have a scalar quantity. You say that now I
Hmm.
define a surface, any surface where your phi is constant, right?
Hmm.
Now, what this okay, so what this is telling you is now you have this surface where your phi is constant. It is telling
Yes.
you that if you know, like, then the equation for this surface will be like something like phi equal to some c. Now,
Hmm.
gradient of phi, it is telling you that show that gradient of phi, which is a vector, is perpendicular to the surface, right? Which is along the normal to the surface. How can we prove that? So what we can do is we can take a small position vector in this surface, okay, given as r like r equal to x I cap plus y j cap plus z k cap. So this is the position. So if you have a point P on the surface and the position vector is x, y, and z, okay. So now if you take a small differential like dr, it will be dx I cap plus dy j cap plus dz k cap, right? Which will be, what will be the direction of that vector? That is basically the tangent plane to the surface P at P. So basically at this point
Hmm.
P, whatever be the surface, now if you draw a tangent, that is this vector, right?
Yeah.
Now, what is like if you have any function phi, okay, and you know that phi depends on x, y, and z. Now we know from our ideas of partial derivatives that if you say that phi is constant, then we can write d phi equal to 0, right? And what is d phi? D phi is basically del phi del x into dx plus del phi del y into dy plus del phi del z into dz, right? That's how you can define a differential, which depends on this variables. And it is equal to 0 because on this surface phi is constant, right? Now, this, the left hand side that you have here, this is nothing but a dot product of gradient of phi into this differential, right? So if you had the
Yes.
gradient of phi, which is this, and then this is your
Hmm.
differential, so this is just the dot product of the two.
Just the dot product. So it will be the
Yeah.
result. Yeah.
Yeah. So that means this is telling you that if this is a vector, this is also a vector, and their dot
Hmm.
product is 0. That means the angle between them is 90, right? So del phi, that means the direction which comes from the gradient of phi is
Hmm.
perpendicular to dr, which lies on this surface. So that
Okay.
means del phi is perpendicular to the surface where phi is constant. So that means if you have any scalar field, and if you define a surface where the scalar quantity is constant, okay, define some surface, then del phi will be in the direction perpendicular to that surface. Okay.
Okay.
So basically, if you can consider like, uh, like field lines, right? So if you have,
Hmm.
or like wave fronts, if you have multiple wave fronts, and then you can draw normal to that wave fronts, right? So it's like that. So if you have multiple surfaces where, suppose if you have some surface where phi is changing like this. So like all of this surface corresponds to some constant value of phi. Like consider this to be some surface, okay? These are not lines, but surfaces. Then the normal at each point, like, the normal to these surfaces will be your del phi. Clear?
Okay.
And that's the direction of along which your phi is having your maximum change. So now if you want to say how your quantity is changing in some other arbitrary direction, then you take a dot product of del phi with that vector. Okay. Now you can also use it for many other types of questions. Like suppose if you have a surface like surface equation is given like this, x square y plus something at like some equation of a surface at a given point, you are asked to find the unit normal to the surface. So this can be a typical mathematical physics question, or it can come up in many situations. But what this idea of vector algebra is already telling you is that you can just do a gradient of this quantity, right? So if this is your surface, do a gradient that gives you the vector in the perpendicular direction. And if you want a unit vector, just divide by the magnitude, right? So that gives, so for any surface, you can use this idea to find the normal to the surface. Now, moving on to uh, divergence, right? Now, what does divergence tell us? Like, what is divergence all about physically? Like, what's the physical significance? So for this, what you can consider is something like this. So consider a vector field now. Okay. So one such example, a very common example, is a velocity field. So if you have some fluid in a container, it's moving. So it has some fluid velocity. Okay. And at a particular point, you can define the velocity as dx by z. Now, what this is telling you is that now the v is not constant everywhere. Okay. So we consider that the v can change along x, it can change along y, it can change along z. Now, if we take a small volume element, okay, where the dimensions are delta x, delta y, and delta z. So this is your volume element. And if you have a small point P at the center of this volume element, P of x, y, z, okay, and it is said that, so the fluid is flowing, right? So there is an inflow of fluid and there is an outflow of fluid from here. So at point P, if we define the velocity along the x component as v1, right? And if we say that your v1 depends on x, okay, the v1 changes with x with a rate given as del v1 del x, then we can say that if the velocity here is v1, the velocity here will be slightly less, where velocity here will be slightly more, right? So you can say that the x component of velocity at this surface, like this surface is like a, like here, right? AFED. So this surface, you can say that the velocity is given as v1 minus half of, why half? Because you have taken point P at the center of your volume element, right? So basically
Ma'am,
this,
can you repeat why half?
okay, so basically you know the velocity at this point, right?
Yeah.
And you
Yes.
know how your velocity is changing along x. So if
Yeah,
you know
because of
the
the flow
velocity
of
at
the
this,
fluid.
yes, so if
Hmm.
you know the velocity at the center and you know the
Hmm.
rate at which velocity is changing along x, if you are asked what is the velocity at this point, ignore my list, like basically this point, or what is the velocity at this point. So what will you do? If you know the rate and you know the distance it has moved, right? So you just multiply by that, right? Del V1 del X is your rate, and you multiply by
Yeah.
the distance between the two, and that will be
Distance.
nothing but
Yeah, yeah.
delta
Okay,
x by
okay.
2, right?
Understood.
So that's
Okay.
how. So you can write that the velocity at one face will be given by this relation, while the velocity on the other face. So if like once you calculate on the like inside surface, and then you can also calculate on this surface, right? This surface, basically BGHC, right?
Ma'am, on
And
BGHC, it will be same only, right? Because there won't be any minus, so it will be like V1 only.
no, it can add up, right? We are saying that you have a velocity at a point,
Huh.
and you know that
Yeah.
the velocity changes along x. So obviously,
Okay.
if point P is at x1, suppose
Yeah.
this, like if this corresponds to x1, then this
Hmm.
edge obviously has like x plus something, right? While
Hmm.
this is at x minus something. Clear?
Hmm.
Now you
Hmm.
know the velocity at the central point. So you can also tell the velocity at the other surface and what's the velocity at the front
Other
surface,
side.
right?
Concept.
Yeah. So
Hmm.
that's what you're doing. So you're trying to find the x component at
Hmm.
the two faces. Now,
Yeah.
similarly, you can have, velocity components along like the y component or the z component. All of them can have these variations, right?
Yeah.
So you can do similar things for this surface and this surface again, like all the surfaces, considering that your velocity changes along x, y, and z, all of it, right? Some with
Yeah,
some
but in
variation.
this particular question, velocity is changing only on the x component, right?
Like in general, you can have changes
No,
along all the directions, right?
no. For example, in this particular question, the like velocity change in velocity is happening only through the x component, right? Because the water is like through the x component. So for y component and z component, there won't be any
No, no,
velocities,
no,
right?
no, 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 no.
Then
What I'm telling is that
okay.
consider an arbitrary velocity vector. Okay, see, the velocity is
Yeah.
not just along x. Like
Hmm.
it's just how the picture has been drawn, but it's not that the velocity is only along y. Like here, this is y, so it
Okay.
doesn't mean that the velocity is only along y. Okay, take a
Hmm.
very simplified condition where you have some velocity vector which has x, y, and z components. Okay, and they vary along all the three directions x, y, and z with different rates, which is given by the partial derivatives, right? Del v1, del x. Similarly, you can have like del v2, del y, del v3, del z, something like that, right? Hello?
Right, ma'am. Right. Sorry, I was
Yeah, yeah.
mute.
So now what we are trying to do is, so by using this idea of the partial derivatives, right? Because we know how this thing is changing as we go along x, y, or z, we can tell what is the amount of net fluid that is coming in and what is the amount of fluid going out, right? So in a way, what you
Right.
can find is you can find, so if this is for like you know how the velocities are changing. So from here, you can try to find the volume of the fluid crossing the different surfaces. Okay. And the difference of the two will give you the net amount of, you know, change in volume that has happened in a particular direction. Similarly, you can do it
Yeah.
for
Change
Y.
in volume.
Yes.
Yeah.
Similarly, you can do
Understood.
for Y or Z.
Y
Now,
direction and Z direction. Okay.
yes. So now if you do total loss in the volume, what will you do? You will add up all of them, right? So if you, and then per unit volume, so you divide by the net volume. What you end up getting is divergence of V, which is the divergence of your velocity field, right? So basically what this is telling you is that divergence has this information whether there is a net flux of that quantity in that region or not. Right. Suppose divergence is zero. What would that mean? That there is no loss. That means whatever is going in is like whatever is going into this volume is also coming out from the other end. So the volume is conserved. Right. So in a incompressible fluid, this is what we have. We have this continuity equation which tells us that your velocity field is divergenceless. Right. So in a way, divergence physically has this idea of how what is the net flux line that is going past that point, right? If there is a non-zero quantity, that means there is a net flux. If suppose what we will talk about it as we proceed. If there are cases where things come out and then come in and go out at the same rate, that means the net flux that is crossing that point is zero, right? So in those cases, your divergence will come out to be zero, right? So when you have a vector whose divergence is zero, we call them as solenoidal, right? So there can be many questions, very simple questions, where you are given some vector and you are asked whether that vector is solenoidal or not. So just try to find the divergence, right? If it is zero, it's solenoidal.
Okay, ma'am. Understood.
Yeah. So suppose if you have a question like this, okay, so you're given some vector and it said that it's solenoidal. Now you have to find what this variable A is. So this is very simple. So what you do, you find the divergence and you equate. So basically you do divergence. Now we know that divergence should be zero. So that gives you the value of A. So all this kind of simple, vector algebra problems can come up from this concept. But what's more important to remember here is this physical understanding of what divergence physically mean. So later we will see that, in we always know that, magnets always exist in pairs, like you have a north pole and south pole together, right? So we know that there are no monopoles in magnets, and because of that, we would later see that divergence of B will always be zero, right? So that is because the field lines start from one pole and come back to the other pole. So there's no net, flux that is there, that is at
No
a
loss,
particular point.
basically, right?
No loss or no
Yeah.
difference in how, what
No,
is the
no
in.
difference.
Yes, exactly.
So the magnet doesn't have any divergence, is what you're saying.
Yes, exactly. So
Okay.
we'll later see that this is a very fundamental law which will come up, that
Hmm.
while electric fields can have a divergence, because you can have a separate positive charge or a separate negative charge, right? But not for magnets. Now, regarding curl, what is curl? Now, as it already comes up in the name, it talks about how the field lines rotate, whether there is a net rotation in your field lines or not. Okay, so if you have a field where the field lines are straight, there is no curvature there. Okay, so in that case, the curl is zero. Now, it has a lot of significance. Okay, so when you have a vector whose curl is zero, it results in very fundamentally situations where we talk about conservative forces and things like that. So as we proceed, we'll talk about it. Okay. But for now, if you have to visualize, we can say that if you have a vector and the curl goes to zero, that means the field lines are straight. There is no curvature there. Okay. And this is just a convention. You can, like, how much it is circulating. So you can take counterclockwise as positive, clockwise as negative. These are just conventions. So now, suppose if you have a vector, and if the curl goes to zero, we call it irrotational. Okay. So it says that you have a vector. It's my, okay. So suppose it is said that you have a vector, it is irrotational. So curl of V goes to zero, and this is the form of your vector. Okay. We have to find A, B, and C so that it goes to zero, right? So what do we do? So we can apply our well-known idea of cross products. Okay. So we would have different equations. Okay. And then we would equate and try to find what ABC is. That is very straightforward, right? Basically, this is your equation. Now, this should be equal to zero. This should be equal to zero. This should also be equal to zero. So that gives you the value of A, B, and C. So these questions are very straightforward. What is more interesting is the next part of the question, which says that if V is irrotational, that means if the curl of V goes to zero, show that V can be expressed as a gradient of a scalar function, right? What it means is that now you can write V as something like this. Okay, so you know V, and because V is the curl of V is zero, it is saying that show that you can write V as gradient of some scalar phi. Okay. So now let us assume that we can write it this way. So V is equal to gradient of phi. Let us assume this. So from here you can write an x coordinate, a y coordinate, and a z coordinate. Right. Now what you get by comparing this with this is you get an equation for del phi del x, you get an equation for del phi del y, and you get an equation for del phi del z. Clear till here? We are trying to prove that you can do that. For that, we have assumed that this
Yes,
is true. Yes. So now what you do is, now you compare these three equations. So from the first equation, okay, you want to find phi. Ultimately, you want to find phi. You want to say that, yes, there is a phi that exists. So for that, what you do, now this is the relation. So you say that you integrate one partially with respect to x. Okay. So what do you get? Normal integration. And then you say that there can be a constant, some constant, which is a function of y and z, right? Where f, y, z is an arbitrary function of y, z, right? Now, similarly, from this equation, equation 2, you can again integrate partially with respect to y, and you can get an expression for phi. And similarly with the third, right? So something like this. So by integrating with respect to x, you get this. From the second equation, you get this. From the third equation, you get this. Now, if you compare all the three, okay, so what you see is, see here, like some terms are common, right? Like here, you can see x squared by 2, 2xy plus 4xz. Again, when you compare with this, you have again the 2xy term, okay? There is this term coming in, minus y squared by 2 minus yz. This is an extra term coming in, right? Again, here you can see, again, 4xz is already there, but there is another 2 extra terms here, right? So now if you compare all the three expressions, you get a final expression for fyz, like what your fyz, gxz, and hxy should be, right? So in, like, by comparing all the three, you get a final expression for phi. Now you have to remember that you can add some constant to this phi, which does not make any change because gradient of a constant will always be 0, right? So with this freedom of adding any constant to it, this is your expression of phi. Okay, so that means when you have a vector which is irrotational, you can write it as a gradient of some scalar quantity like this, right? Clear till here?
yes.
Yeah. So now this is very important and very fundamental because this is telling you that you have now got a new quantity. So see, whenever you are dealing with vectors, you have to deal with, their position, their directions, their magnitudes, and all the different components separately. If there is a way where you can move from a vector to a scalar quantity, which is much easier to deal with, it's always simpler, right? So this is telling you that if you know that your vector is irrotational, if the curl is 0, you can basically move from your vector to some scalar quantity phi, okay, where v is equal to gradient of phi. And this is the idea behind having a scalar potential. So if you say that if you have a vector which is irrotational, you say that it's a conservative vector field, and there you can define a scalar potential phi. Okay. Now, the same concept came up
So,
in
ma'am, the irrotational thing means basically that there is no curvature in this, like no curl in the field line.
yes.
Okay.
Basically, your curl goes to 0. Now, physically try to understand that what this has a huge implication, that if you have a vector whose curl goes to 0, you can rewrite that vector in terms of a scalar now. Okay.
Scalar.
And
Hmm.
yes, that scalar is your scalar potential. This
Hmm.
is the same concept which comes up when we bring in the concept of electric potential, right? So we
Okay.
would see that if you have, as long as we are in electrostatics, we would see that electric field will turn out to be irrotational. Okay. And when
Irrotation. Hmm.
electric field will turn out to be irrotational, we can actually write electric field in terms of gradient of a
Scalar
scalar,
potential.
which is your
Hmm.
potential. When we define potential, that's how this concept of potential came in. Okay. So
Okay.
when you have a
Okay.
conservative vector field, you can write that vector in terms of gradient of a scalar potential.
Yeah.
Okay.
Hmm.
So let us look at the Gauss's law. Okay. Now, and then as we proceed, we will come to that point where we would define our scalar potential by using the fact that the electric field turns out to be rotational. Okay. To start with, we would talk before that, let us start with the Gauss's law. Okay. So till now we have understood what gradient divergence and curl is, and we have understood their implications. Okay. And with that knowledge, we are talking about electrostatics now, as of now. So
Hmm.
now Coulomb's law, we know this is what Coulomb's law is. Is my pointer gone? Okay. So we know this is our Coulomb's law. Okay. Now, what's important here is that if you have a positive charge, now if you use this, you can actually define how your field lines will be, right? So if you have a positive charge, the field lines emanate from the charge. It's radially outwards. Okay. While if you have a negative charge, you would have field lines coming towards the charge. Okay, because of the direction. It's r cap. If you have a minus charge, it will be minus r cap, which is radially inward, right? It's important to remember this. That if you have a positive charge, your field lines start from that, goes outward, while if you have a negative charge, your field lines come towards that charge, okay, radially inward. Now, from this field lines and the concept of field lines, you can say that what is a net flux. So if you define any surface, what is the net flux of electric field lines going through that surface? What does this flux mean? It's basically how how are the field lines crossing the surface, right? You have field lines. What is the measure of the field lines crossing the surface? That's your flux. Okay. How do you define it? You define it as this surface integral, E dot ds. So if you have a surface and your normal vector to the surface is given by this dA vector, okay, and then you do a integral over this surface, okay, that gives you the net flux. E dot ds gives you the net flux through the surface. Okay. Now you can understand that. So as we have understood that if you have a positive charge, your field lines start from there. If you have a negative charge, field lines come in there. So now you can imagine that if you have some surface, okay, some closed surface, suppose, and then you have a charge somewhere inside. So you can understand that there'll be charges going out from that or coming in, right? So that charge will be a source of field lines. And then, so basically, you have a surface, so there will be field lines crossing the surface. So in a way, the flux by itself can be a measure of the charge that is there inside. So if you have a closed surface with some charge inside, the flux can be a measure of the total charge that is there inside, right? And that lies at the heart of Gauss's law. Okay. What this is telling you is that suppose if you have a closed surface, you have suppose some Q charge. Okay, so there will be field lines going out because of this Q charge. And suppose you have another 2Q charge again here. So there'll be again charges, field lines going out, right? What happens if you have suppose Q and then minus Q? What would happen? The field lines will go out from here and again come in from here, right? So the net flux in that surface will then turn out to be zero. So
Zero. Yeah.
on the other end, if you have a net charge here, you would have a net flux either inward or outward, right? So that means if there is a net charge inside a closed surface, like in the region enclosed by a closed surface, then you would have a net flux through that surface, right? Now, to understand that mathematically and like in a simpler version, what we can do is we can consider a point charge at the origin and then consider a sphere of some radius r. Okay. And we can try to do the scale, like the surface integral. Okay. So 1 by 4 pi epsilon 0 q by r square r cap. And then we take a surface element, which is r square sine theta d theta d phi. So this is in the spherical coordinate, a small surface element. Okay. And we do an integration over it. So when we do, what do we get? So basically 2 pi will be like d phi will integrate to get a 2 pi and then 2 pi and then you have sine theta d theta. So basically this will turn out to be 4 pi r square, right? And again, this r square will get cancelled. So at the end of the day, what you'll be getting is q by epsilon naught, right? So this is telling you that the net flux through that surface of the sphere is equal to the charge that was inside by epsilon. Now, This is a simplified version. You don't have to have a sphere. Basically, this is true for any arbitrary shaped surface. Okay. So the flux through any surface enclosing the charge will be equal to Q by epsilon naught, where Q is your charge enclosed. So if you have multiple number of such charges, you can use your superposition principle, and then this will be the relation that you will get. Okay. Now this will be a very useful relation because this will save us a lot of time, lot of effort. Okay. And this will fundamentally lead us to new relations, which will be very useful. Okay. Now, this is in the integral form, right? You do a surface integral equal to Q enclosed by epsilon. You can also write the same relation or the same law in differential form. Okay. So what you can do for that is you can use this divergence theorem. So this is a well-known theorem in vector algebra, which helps us to go from a surface integral to a volume integral. So it tells us that if you have a closed surface that will enclose a volume, right? A closed surface will enclose a volume. Is that clear? So you can write this relation that E dot dA, which is the surface integral, will be equal to divergence of E into dV or d tau, which is your volume element. Okay. So this is the well-known divergence theorem. So now what you can do is so this is what you have, right? So now you can change this surface integral to volume integral. Similarly, you can change this definition of Q enclosed to a volume integral. How do you do that? So you say that the charge density, charge per unit volume is rho. So the net charge will then be rho d tau, an integration over the entire volume, right? So you can replace Q enclosed by this relation. And similarly, you can replace the left-hand side by this. So this is what your Gauss's law then becomes, right? Now you have volume integrals on both sides. So this gives you, if you compare the two, this gives you this relation. So this is again the Gauss's law, but now in the differential form. So this tells us that divergence of E is equal to rho by epsilon naught. So now again, if we physically understand what is it, divergence of electric field, okay, is related to the flux. Okay, what is the influx, what is the outflux, and that has to be related to what is the charge, right? And that is what you get. Divergence of E is equal to rho by epsilon naught, right? So this is your first law. Clear? So this is telling you that now if you suppose if you know the electric field, okay, you want to find the charge density. How do you do that? You use this relation. If you know the electric field in the vector form, suppose, so you can find the divergence and you can use this relation to find the net charge density. If you know the charge density, you can use it to find the total charge, right? So based on whatever we have discussed till now, okay, this is a very not very difficult, very straightforward type of question. Can you try to solve it? Try to find an expression for rho.
Yes, sir.
Use this relation.
Yeah.
You are stuck somewhere or there are doubts, please feel free to ask. Okay. So see, it's in spherical coordinates. So you have to write the expression of divergence in the spherical coordinates. So there again, we
Okay.
go back to our idea of curvilinear coordinates, right?
Hmm. Hmm.
Yeah. Are you guys trying, or like should I like go ahead with, like, if you're really
Uh,
solving it, I'll give you time.
one one second,
Right.
ma'am. I'm actually just
Sure.
checking if I can do it.
Yeah, sure. You will be able to do it. See, you have electric field, try to write the divergence in the equation.
Hmm.
And it's a dot product. So all the other components like phi cap and theta cap will go to zero. So only the radial component of your divergence will act on this radial component of electric field, and that will be a scalar quantity,
I'm like
right?
first like we'll like compute the divergence in this thing, no? Spherical coordinates.
Exactly. So what I'm
Yeah.
telling you is that you only have radial component. So other components, like the expressions of other components of your divergence
Yeah,
does
so
not matter.
like we are getting like 5 kr square the divergence. After that, I've like trying to find the this thing charge density. So like that's
That is,
like
so once you
multiply E
find a
naught.
divergence, epsilon naught, yes.
Yeah, so like the answer is like 5 epsilon naught kr square.
Okay, so
Is
let's see.
that the answer?
Yeah, let's see. This is what you're getting, right?
Yeah, yeah.
Yes, exactly.
The
So
second
now,
part
if
I
you,
don't know what to do
so
actually.
second part now, once you know rho, right? Once you know rho, what you have to find? You have to find the total charge, right? So
Okay.
total charge is this, basically. So you know the charge per unit volume. You have to do an
Okay.
integration over the entire volume to find the total charge, right?
Understood.
Yes. So you have to do a volume integral where your volume
Yeah,
integral
ma'am,
for a
that
sphere.
yeah, so ma'am, like volume integral for the this thing, spherical coordinates I did. So like so I did that and I found the answer. But like, what is the second way actually? Like it's written that do it in two different ways. So I'm not understanding what the second way here.
Okay, so one is,
The volume
basically
integral one.
this, right? Another
Yeah,
is
that one I've
directly,
done.
yeah, another is directly by the Gauss's law. Basically,
Okay.
if you know the electric field and you know the volume, like basically either you do volume integral or you do surface integral, right? So this is the
Hmm.
volume integral part. You can also do surface integrals. So you know electric field,
Hmm.
you know your like area for the sphere,
Hmm.
right? So from there you can find the net enclosed charge.
Okay, understood.
Like, just this is just to get used to this connection between the the surface integrals and the volume integrals, like, so that you remember
Okay,
this thing. Yeah, this
this
is the
thing.
main.
Okay.
Yeah, this thing is what you have to be used to. So
Hmm. Understood. Understood.
Okay. So now there can be questions like this, which is like a very standard question. Okay. Where you say that you have a charge at one point of your, I'm always losing my cursor. Yeah. So you have a charge somewhere at one corner of a cube, and then what is the flux through the shaded side,
Electric field.
right? So
Hmm.
here, any idea how to do it?
No, ma'am. Sorry.
No, nothing to be sorry. We are learning. So basically,
Yeah.
what we have to do is, so we have to enclose the charge, right? We want to find flux. So, and we want to use Gauss's law because we saw that if we can use Gauss's law, we can directly relate flux to the charge enclosed, right? So now if we want to use Gauss's law, we need to enclose the charge. The charge is sitting on one corner, right? So what can we do? We can make use of the symmetry that we have in the question, and we can add in a number of more cubes like this so that your charge sits at the center of that combination of cubes, right? Something like this. Okay. So you, in question, you're given this, right? What you do is you add cubes on all sides like this so that your charge, which was initially at one corner, now sits at the center of this new cube that you have got. Clear? So now it's basically a very simple Gauss's law problem, right? You have a charge q at this, like inside a bigger cube. Now the cube has, so if this was, suppose the area is A, so you would have here how many such surfaces are there, right? So you have 4 such surfaces and then 6 of them, right? So total you have 24 such surfaces, which is enclosing it, right? So what you can then say is that E dot dA for this surface, the flux that is crossing through this surface is 1 by 24th of the whole large cube, right? And what would be the flux through the whole cube? That is nothing but q by epsilon naught, which comes from the Gauss's law, right? So therefore, for this case, for one surface, you would have it as q by 24 epsilon naught. Is it clear?
Yes, ma'am.
Okay. Okay. Now there can also be questions like this where you again use the Gauss's law, but in different kinds of, so based on the question that you have to choose your, coordinate system. Like here, or the Gaussian surface. So here you have a long cylinder and it carries a charge density which is proportional to the distance. So you say that it has a net charge and the charge is varying radially in this direction, right? Which is given by this relation. It's proportional to the radial, like the radius. Now, the electric field inside this cylinder. Okay. So this will tell you how this Gauss's law is so useful when you have questions like this, when you can make use of the symmetry, and you can use the symmetry and the well-known integrals to find the net charge enclosed and things like that. So for this, what you do is you have to find inside the cylinder, right? So consider a Gaussian surface, some arbitrary Gaussian surface of some radius s, right? So this cylinder will have a curved surface area like this, and there'll be 2 such radial surfaces as well, right? So total 1 curved surface area and then this 2 circular areas. Now this is your Gaussian surface. Okay. So what we can tell is that if we can find the flux that is going through this Gaussian surface, okay, whatever we have considered, then we can actually find what the electric field will be at this distance from, like, at this radial distance. Is it okay to say that, right? Because if we can find the charge enclosed, then we know the, basically we know the flux. If we know the flux and if we know the area, we can find the electric field, right? So what we will do is, we'll consider a Gaussian cylinder of length L and radius S, which is as shown here, right? And we would use the Gauss's law, which tells us that for this surface, E dot dA will be equal to Q enclosed by this surface by epsilon naught. Now, what is the Q enclosed by this surface? So you put in your value of rho, which is given here, right? And then you write your volume element in the cylindrical coordinate system, right? So your volume element in cylindrical coordinate system is given by this relation here, S ds d phi dz, where S is your radial coordinate. Okay. So if you do that, you can find an expression for the charge that is enclosed inside this Gaussian surface. Okay. Now, once you know that, you know the right hand side of this equation. Okay. So what you have to do now, you have to find this part. Now here, if you make use of the symmetry of your problem, you can say that so for this dA, right? So you have three such things. So you would have a dA in this direction for this surface, this circular surface. Again, for this surface, you would have a dA in this direction. And then for the curved surface, you would have perpendicular to this, right? At each point, there'll be vectors coming out like this, right? Now, from the symmetry, we can say that the electric field should be along, like what matters is this curved surface area, right? Because this effects will get cancelled because of the radial symmetry that we have, okay? So this tells you that now we can write E dA as, E into 2 pi SL. 2 pi SL is nothing but the curved surface area of your cylinder. Okay. So if you do that, E into 2 pi SL is equal to the net enclosed charge by epsilon naught. And that is, from here, you can basically find the electric field inside the cylinder. Okay. Now, if you put S equal to this, total, like if you have some radius R, that like, then it would be the total charge that is there in the cylinder. Okay. So that's how you can use Gauss's law to find electric fields. There can also be questions like this, okay, where you have a hollow spherical shell which carries a charge density given by this relation. In the region, like in this region, basically between A to B, okay, this place is hollow. Now you can try to use Gauss's law to find electric fields in all these three regions. Okay. Now, if we look closely, and it's very easy to say that in this region, anywhere inside, if we consider a Gaussian surface, what would be the net charge that would be enclosed? 0, right? Because there's nothing here. So anywhere inside, that is R less than A, there is no charge enclosed. So that already tells you that your electric field is 0 here, right? Now, when we are between A and B, we would have some charge enclosed based on this charge density, right? And that can be used to find the electric field in the inside region. For outside, what would happen? The entire charge that is enclosed by this hollow spherical shell will then contribute, right? So let us look step by step. So, there's a lag. I don't know why this lag is coming. One second, there might be some lag in this. Trying to change, but nothing is changing. Yeah. So in the first case, your electric field is 0 because Q enclosed is 0. For the second case, what do? We consider a sphere. Like wherever you have to find your, electric field, you have to consider your Gaussian surface accordingly. So for R less than A, you have to consider a Gaussian surface where your R is less than A. When you want to find the electric field between A and B, you have to consider a Gaussian surface here, basically with a radius somewhere between A and B, right? Somewhere here. Now, for that radius, you can say that E into 4 pi r square, which is your surface like integral, should be equal to Q enclosed by epsilon naught. What will be your Q enclosed? Rho d tau by epsilon naught. Now rho is this, which is already given. And then now d tau, which is your volume element, has to be written in terms of your spherical coordinate system, right? So if you do that, you find an expression for the electric field, which again says that now it's a non-zero value, which is again varying radially. Okay, so this is your value of electric field somewhere between A and B. Similarly, now for R greater than B, okay, so then you consider a Gaussian sphere outside. Okay, now here you have to remember, see, here you had done an integration from A to R, which was your selected radius. But anywhere outside, anywhere R greater than B, there is no charge beyond B. So now your integration will change from A, like it would be only till B, right? Because anything beyond B, there is no charge, there is no rho basically, right? So that means now again you can write it as E into 4 pi r square, but this time the integration in your volume element should be from A to B. Okay, so this is your electric field outside. Okay, so what you can then do is you can try to plot it, and it would have a expression like this. Now there can be, based on this kind of question, now what one can do in a question is your A and B can actually be, numerical values, 5, 10, something, right? And then you might be asked what is the electric field and things like that. So there you have to use similar concepts, but then obviously it will give you some values because you will have some numerical values for A and B. So in the previous year questions, I did see questions like this, but there were numerical values that were substituted in this region. So, but the way of working out these problems is like this. Okay. Now, this was about some questions on how we use Gauss's law to find electric fields. Now let us go back to this very interesting idea of curl of E and use this idea that when you have a vector whose curl goes to 0, how can we write it in terms of a scalar potential? And that gives rise to our very well-known idea of electric potential. Okay. Now we are talking about electrostatics. So there, what we can take a simplest, example is a point charge, and the field for a point charge is given by. So what we can now try to do is we can try to find a line integral from some point A to some point B. Okay. For this, what do? We know the electric field. We define a line element. Now the line element is spherical coordinate like this, right? The electric field is only in the radial component, so only the dot product with dr will survive, right? So you'll get E dot dl given by this relation. Now you're going from A to B, so you try to find the integral and you get the result as this, right? Now what this is telling you is that now if you put RA equal to RB, that means if you come back to the same point where you started, okay, if it is a closed path, this term goes to 0, right? So that means the integral around a closed path goes to 0, okay? Why it is interesting? You can use this well-known Stokes theorem, which can enable us to go from this line integral, closed line integral, to a surface integral. Okay, so you can write a closed integral of A dot dr, where dr is your line element which encloses a surface, should be equal to curl of that vector dot ds. Okay, so now you're going from line integral to surface integral. Initially, when we are talking about divergence theorem, we are going from surface integral to volume integral. Okay, so now what this tells us is if you now use this relation, it would tell you that curl of E is 0. Right? Our last example that we had tried to see, we saw that if you have a vector whose goes to 0, you can define that vector in terms of gradient of a scalar quantity. Okay, so basically now you can write E as gradient of some potential V. This minus sign is a convention, what we call our electric field. what it tells us physically. Okay, what is this electric potential? Okay, so let us look into it. So when we say that the line integral goes to 0, that means what this is telling you is that if we do a line integral from a to b by this path or by this path, okay, overall this is a closed integral. So overall a to b and then b to a should be giving us a zero value in the integral, right? So if we break it up, we can write, yeah, yes.
Please use the laser pointer, ma'am, so that we can follow where on the page you are talking about. Yes, ma'am.
Yeah. So I think till now it's clear, right? Whatever we discussed. So it is that. So this tells you that your line integral goes to 0. Using the Stokes theorem, you can rewrite this as this, which tells us that the curl of electric field is 0 when you're talking about electrostatics. Okay. Now, what this can also tell us is if you have a line integral which is 0 over a closed path, you can rewrite it as telling that the amount or the line integral from a to b, whether we follow path 1 or path 2, does not make any difference. Okay, it's independent of the path. The line integral is independent of the path. Okay, so now if you define a quantity, okay, some quantity v, which is this line integral value. Okay, so you start from some standard reference point which is given as o, then that is your origin, and from the origin to some point r, you can come from whatever path you want to take. This value will be a unique value. Okay, you can add some constants to it, but otherwise it's an unique quantity. Okay, this is what we call the electric potential. Okay, so now if we have this definition, what we can do is you can write the potential difference between 2 points b and a, right? So this is going from some origin to b, this is going from some origin to a. You want to find the difference between the two, so this is what you get. Basically, this is a line integral from b to a. Okay. Now, based on our understanding of gradients, what is gradient, right? If you have some scalar quantity which is varying in a particular direction, we know that how much is the variation? That is vb minus va. And that is nothing but the dot product in that direction, dot product of gradient of that quantity in the dl direction, right? So this is from our standard definition of vector algebra. Okay, but now if we compare this with our initial definition that we take, what do we get? We get that electric field can be written as minus of grad v. Okay, so again, what you are writing is you're writing your electric field in terms of gradient of a scalar quantity now, and that scalar quantity is your electric potential. Okay, so the fact that in your in electrostatics, the curl of your electric field goes to 0 allows us to define an electric potential. Okay, and that is very useful because now that means you can actually find the potential, which is a scalar quantity, much easier to deal with. Okay, and then once you know the potential, you can actually use this relation to find electric fields. Okay, so that's how the idea of electric potential or scalar potential comes up. Now you can also rewrite your the Gauss's law relation by using this. So from the last definition, we saw that E can be written as minus grad V. Okay, and then you can write divergence of E as rho by epsilon naught, which is from the Gauss's law. Curl of E goes to 0, right? So now by using the relation of vector algebra, you can say that divergence of E can be written as del square V, and then like minus of del square V. So this is what you end up getting. So now you are writing Gauss's law. Okay, you are rewriting Gauss's law in terms of the potential, the electric potential. So this is telling you that if you know the electric potential, which is a scalar quantity, you can use the Laplacian operator. You can find del square V, and if you know del square V, you can use it to find the charge density. Okay, if you know V, you can use this relation to find electric field. Okay, so all this terms now get connected by these different relations. Okay, this equation here is called the Poisson's equation. In regions where there is no charge, that is where rho goes to 0, del square V goes to 0. Okay. So this is called the Laplace equation. So all this, like whenever there's a function which satisfies this relation, the Laplace equation, those are called harmonic functions. So what I saw in the last year's assignment questions is that there were questions like some function is given and it said that whether it's a harmonic function or not. So how do we know that? So you can try to evaluate del square V and see if it goes to 0, it's a harmonic function. Okay. Now, till now, okay, based on whatever we have studied about, electrostatics, this is the relation we get. Now we can relate electric field to the, volume charge density. We can relate electric field to volume, potential, and vice versa. If we know rho, we can find V, okay, by using this relation. If we know V, we can use the other relation to find rho. Okay, so all these relations are intertwined with each other and can be used to find one value while we know the other. Okay, so that's the heart of what we had been discussing till now. Now, there can be, this is always true, this is there, but now, based on the medium that we are dealing with, okay, there can be different kinds of, like one can define the charge density in different ways. So one is you put in some charge, right? You bring in some charge. Suppose you have a region, now you bring in a positive charge. So that is in your control, okay? That is there, that's your free charge. But the presence of this free charge can affect the medium around it, okay? So suppose if you have, we know about this, like, I hope briefly we know about it, is this idea of polarization, right? So if you have some polarizable material and then you have an electric field, so there'll be a net induced polarization that can get developed, right? So there can be bound charges, which is coming because of this polarization. So you have a free charge, the effect of the free charge results in some rearrangement of the charges that are there in your medium, okay? And that can result in a net bound charge, okay? So in that case, a more general way of defining your charge density would be rho, which has contributions of bound charge and contributions of free charge, right? So then the Gauss's law can be rewritten as replacing rho by rho B plus rho F, okay? Now, later we can look closely into how we can define this bound charge, but one way it's clear that this bound charge is related to the polarization of the medium, okay? So we'll come to this derivation later, but for now, what we can tell is that this is how one can relate the, like, take it with a, for now, take it as a information. Later, we will try to derive it. But the point is that the bound charge is related to the polarization of the material by this relation, okay, where P is your polarization, okay. So now what you can rewrite is, you can take this to the left-hand side, and this is what you get, okay. So you get divergence of this new quantity, epsilon naught E plus P, which is equal to rho F, where rho F is your free charge, okay. The information about the bound charge comes in the polarization. So this new term is what we call the electric displacement, D. Okay. So that means the same Gauss's law can now be written as divergence of D equal to rho F, where rho F is your free charge. If you want to rewrite in the integral form, it would turn out to be this. So here you can see it's similar to what we had before, but the epsilon naught is being taken care of already here, right? It's already taken care of in the definition of your electric displacement. So if you know the electric displacement, if you do a surface integral, you directly end up getting the enclosed charge. Clear? So this charge is the free charge. So let us look at this example. Okay. So here it says that you have so here it says that you have this straight wire, okay, carrying some uniform charge lambda. It's surrounded by a rubber insulation of radius A. Find the electric displacement. Okay. So what this is telling you is, now you can use the Gauss's law again. So you consider a cylindrical Gaussian surface. Okay. So somewhere inside, if you want to find the field somewhere inside, what do? You consider a Gaussian surface of some radius S inside. So then D into 2 pi SL, which is your curved surface area along this cylinder, right? So D into 2 pi SL will be equal to what? Just the charge enclosed, right? So if your charge per unit length is lambda and your length of your Gaussian cylinder is L, then the charge enclosed is lambda into L, right? So therefore, D is given as lambda by 2 pi S. So this is your expression of electric displacement at a distance S from the axis of your cylinder, where lambda is your charge, line charge density, okay? And S is the distance from the axis. This is how you define your electric displacement. Now, if you are asked to find the electric field, right? So there, what you have to do, you need to know the information about your polarization, right? Because you know D, you want to find E, so you need to have an idea about P. So if your medium, suppose if you want to find the electric field here, somewhere outside where the medium is free space, so there is no polarization, so P goes to 0. In that case, you can directly use this relation. If you know D, you can directly use this relation to find electric field. Okay. But inside where you have suppose rubber, which is a material, right? So it can have a net polarization. There we need to know P in order to go from D to E, right? In free space, you can directly relate D with E by using this relation. So you can see this relation is same as the relation that we had initially derived for a infinite line charge. What's the field at a distance S from the line charge, right? So it's that same expression. So there can be very typical questions which make use of this formulas, right? So there can be questions where the charge density is given, line charge density is given. It is said find the electric field, electric displacement at a distance, suppose 10 centimeter, 10 meter from that line charge. So then you have to use this relation that we have here, right? Okay. Now there can be questions like this where, suppose here, so you have the electric potential in free space, okay, where the charge density rho is 0. So what this question is telling you is that you have a functional form of your potential and it is saying that rho is 0, right? It says that the x component of electric field Ex and V are 0 at the origin. So these are the different conditions that are being already provided in your question. Okay, Vx is given, rho is 0, Ex and V are 0 at the origin. Okay, you have to find Fx. Okay, so in order to address this kind of question, how do we start? So what is given? V is given, rho is 0. So what is the relation that relates V with rho, right? Let's start with that. What is the relation that relates V potential with the charge density, right? So can you tell me what the relation is?
That del square V is equal to rho.
Yes. So del square V is equal to rho by epsilon naught, right? Minus rho by epsilon naught. So if this is your relation, so now in the question it says that rho is 0. That means it is telling that del square V is 0, right? So you get a condition that this is your V, del square V is 0, and Ex and V are 0 at the origin. So if you put X and Y as 0, right, V should go to 0. Clear? And Ex is 0. So now what is the relation between E and V? They are related by the gradient, right? E is equal to minus grad V. So now if we use all these relations, what do we get? So this is your V, rho is 0. So we do a double derivative and this gives you this relation. Again, Ex is 0 at the origin. E is equal to minus grad V. So that gives you an expression of Ex. Okay. We put Ex is 0 at the origin, so put x and y as 0. So that gives you a value of the derivative of f at 0. Okay, this is what you get. Okay, now again v is 0 at the origin, so if you put that, you get an expression of f at the origin. Okay, so now with this given conditions that we get from the question, we can now solve for this equation. Basically, it's a you know second order differential equation. So now you can try solving it. Okay, and do the integrations and get an expression for f. Right, pretty straightforward. So in this kind of questions, we have to look for which are the relations to start with based on the information that is given in the question, and like proceed with using them. Now, another question could be the electric potential in spherical coordinate is given. So your phi or the V is given. Okay, and these are constants. We have to find the charge density, right, at a distance. So again, V is given. You want to find rho, right? So you can again use this relation of del square V is equal to minus rho by epsilon naught to find the charge density. Okay, so this is what you have to do. Now here, because it's in spherical coordinates, so you have to use the expression of del square in the spherical coordinates. Okay, so here because it only depends on the radial variable, so you just have to use the radial part, and this is what you end up getting. Now here you put r equal to r naught. Okay, and that gives you an expression of rho. So there can be also questions where your rho is given, you have to find electric field. So then you use the relation E equal to minus grad P to find the electric field, right? Now, there can also be, questions like this where you have a vector field that is defined, okay? And it says that you have to find, there's a circle of unit radius defined by z equal to 1, okay? And you have to find the value of the integral A dot dl, okay, along that circle, right? So uh, can you like try solving it? It's interesting because typically what we will be doing is we will be taking a line element, then put in the values, do an integration all over the circle, right? That's a typical way of solving a line integral. That's true. But in this kind of questions, what's
You have to convert the coordinate system to cylindrical coordinate.
obviously we have to convert to cylindrical coordinates. We have to take a line element, we have to do the integral. That is true. That will always work. Okay, so that's the general way of doing it. But when you have a question like this, what's interesting and what should be taken care of is there easier way of looking at the question? So because it's a closed integral, so when you are talking about closed integral, one must keep in mind the relation that if the curl of your vector goes to 0, right, then the closed integral will always be 0, right? So in this kind of questions, first when your vector is given, try to solve for the curl of the vector. If the curl goes to 0, that means closed line integral of that vector will always be 0, right? So you don't have to always do the integral.
Yes.
Yeah. So here, so that was the reason for giving this kind of questions, because the so this might not always be true. In many cases, you actually have to do the integral, but when closed integrals are given, try to make use of this thing. So similarly, like basically keep in mind the divergence theorem and the Stokes theorem. Okay.
Okay.
So here it's like just by doing the curl, you can see that it goes to 0. That already tells you that whatever be your, the line integral, whatever be the curved line or whatever, the line integral will always be 0. Okay. Now, there can also be questions like this, which is, which is mostly based on how forces act between charges. So here it says that there are 4 charges which are kept on kept at the different vertices of a square of side R. Okay, and then you have a mass m and charge q placed at the plane of the square at a short distance a from the center. Okay, if the motion of the particle is confined in the plane, it undergoes small oscillations with what angular frequency? So basically, it's like this, right? So you have these four charges. You have a small charge here with a mass m, and it says that it undergoes small oscillations. What is the angular frequency of the oscillation? So in this case, what should come to our mind to start with is that if if there are small oscillations with a particular frequency, i- it must have a restoring kind of effect, right? So the net force is expected to have a form like something like minus kx kind of form, right?
Yes.
So what we can do is we can try to find the net force on the charge. So these are quite straightforward because it's just that we know the distance, we know what are the components. So here only these components will survive, the other components will cancel out. So we'll only have components along y. So we do it for these two charges and similarly for the other two charges, right? So E1, 2 and E2, and the other for the other two, it will be directed downwards. So from there we get a net effective value of electric field, and then if this is the form of the electric field, we can get a value of the charge, which is nothing force, which is nothing but q into the electric field. And if so, here a is your distance, like a is your displacement vector, right? It was displaced by a distance a, right? So if as you can see here, the force has this minus something into a kind of form. So from here you can compare it to the omega square x kind of form and try to find your angular frequency. Okay, so finding forces are quite trivial, but for these questions, you need to keep in mind this part, that when you're talking about oscillations, your force expression should have this minus omega square x kind of form. Okay, now this is a very interesting question. So here it says that you have a charge per unit length on a circular wire of radius a in the xy plane with its center at the origin, and the charge is not constant. Okay, the charge has an angular dependence. So lambda is equal, so you have this cos theta term coming in. So basically what it is telling you is that you have something like this, and then you have a circle, and there is a charge on this circular wire, but the charge is not constant. The charge is changing with angle theta. Okay, find the electric field at the center of the circle. Okay, now for this kind of question, so we can always use our well-known idea of taking a small element, okay, considering what the charge will be, so lambda dl along this wire, and then doing an integration. That we can always do. Okay, but better is when for all these kinds of question, especially when you're talking about this entire idea of EM theory, the idea of symmetry and idea of how the field lines should be, this has to be used. That gives, in many cases, that can give us answers in a much easier way. So here what it is telling you is it has an angular dependence, right? So what you can say is when theta is equal to 0, your the charge is some lambda, right? So it's like some positive quantity here. When theta is 90, this goes to 0. Again here, it's minus. Again here it's 0, something like this, right? So it's decreasing in positive quantity, then again increasing, and that's how it is. So let us first, in this case, look at how, based on my making use of the symmetry, what the direction of the electric field should be. Okay, rather than first finding the magnitude, let us look at the direction. So this is a positive charge, right? So here the field lines should start from, go outward from this point, right? At this point. Similarly here. So you would have a component in this direction, you would have a component in this direction, like this, right? For this point, if you take a small element here.
Yes.
Now, what would happen here? At this point, this is a negative charge. So there, the field lines should come in, right? So
Yes.
again, here you should have your field lines in this direction, right?
Yes, ma'am.
So that means at the center, obviously here the effects in this directions would cancel out because there'll be a symmetric increase, and then like these two will be canceling each other. So the y component obviously will not be there. That comes from the symmetry, right? But what would be the direction is, as you can see, the net field at this point, if you take all the components, because it's a positive half, so it would have fields in this direction, which is the minus x direction. So if this is your x and this is your minus x, right? And because it's a negative sphere, it would again have in the minus direction, right? So now the direction by itself will tell us the answer, right? So it's already telling us that, if you look at all the other options, this should be the one, right? Because your electric field direction at this point should be along the minus x direction. Is it clear?
Yes, ma'am.
Yeah. So that's the best option. So always look for symmetry and think of directions of field lines. That might simplify things. Now, potential inside a uniformly charged solid sphere of radius r and total charge q. This is a very standard question. You can find it in any EM theory book. Okay. So the straightforward way of doing it is you have a uniformly charged solid sphere. So you take a small volume element, which is given as r square sine theta d theta d phi dr. Okay. And then you want to find what the potential is. So this is your relation for the potential, 1 by 4 pi epsilon 0 rho d tau by r. Okay, doing an integration over the entire volume. So here, what is r? R is the distance from the volume element to your field point, right? So you can just use if this is r, this is z, then r should be root over z square plus r square minus 2r z cos theta. These are standard vector, and then once you find v, okay, this is a very general way of doing it, okay, and then you can put in the values based on whatever you have here. So cos theta components can be substituted, and you can do the integration, and you end up getting something like this. Okay, now this I'm going quite fast because this integration is a standard integration which one can solve. But what is important to look at is that this is the expression of potential that one gets. Okay, so now rho is nothing but charge per unit volume. So if your net charge is q by 4 by 3 pi r cube is your rho. So if you substitute that here, you get an expression of potential in terms of total charge and radius of your sphere. So this is your expression of potential for a uniformly charged solid sphere of radius r and total charge q. Now here, if we put r equal to r, right, that would give us the potential on the surface of the sphere, right? So if we do that, what do we get? So this becomes 1, right? So you end up getting q by 4 pi epsilon naught r. So this is it's a very standard, well-known result, and you again get back the same, right? So potential at the surface of a uniformly charged solid sphere with charge q, radius r, is q by 4 pi epsilon naught r, right? Now, what happens at the center? So at the center, if you put r equal to 0, right? So that gives you the potential at the center of a uniformly charged solid sphere, which is 3q by 8 pi epsilon naught r, right? So this results, why I'm particularly pointing it out, is very standard and very useful. So one such question could be this, which makes use of this, values quite well. So here what it says is you have two uniformly charged insulating solid sphere A and B, both of radius A, charges plus q and minus q. Okay. the spheres are placed touching each other. So you know basically the distance between the two centers are very well known. That is, if it is A, so this should be 2A. That is the distance between the two centers. Now, if the potential at the center of a sphere A is VA and that of B is VB, what is the potential difference between the two? Okay. So here what it is telling you is you have two charged spheres. You want to find the potential difference between the two. So one needs to remember that it follows the superposition principle. So if we want to find the potential at this point, it would have contribution of this sphere as well as this sphere, right? Similarly, if you have if you want to find the potential at this point, you would have contributions from this sphere and the adjacent sphere, right? So that means for VA, okay, let us look at VA. So there'll be a potential because of its own potential will also come in, right? Because it's a uniformly charged solid sphere. So what is the potential at the center is given as 3q by 8 pi epsilon naught A. This is what we just got from here as well, right? So that's the
Okay.
potential because of its own charge distribution. And then you would also have contribution because of the other sphere, which is at a distance 2A, right? So that would be given as minus, because it's a negatively charged one, so minus q by 4 pi epsilon naught 2A. Okay, and this is a scalar quantity, so you just add them up. Okay, that makes things simpler. So that's the potential at VA. Similarly, you can try to find a potential at VB. So again, here it will be minus 3q by 8 pi epsilon naught A plus the potential due to this, which is at a distance 2A. So q by 4 pi epsilon naught 2A. So that's the potential at the center in B. So now the difference between the two is given by this relation. Okay, so this result of what is the potential at the center of a uniformly charged solid sphere is something which comes quite handy, and you can also derive it, but it's also quite useful to remember. Okay, so basically that's how one can use the Gauss's law to find electric fields or electric displacements. Okay, so if you are in free space, once you find electric displacement, you can use it to find electric fields. You can use potentials. Okay, in potentials, make use in all of this, make use of superposition, make use of symmetry. Okay, and basically make use of this relation. This is the heart of what we have discussed today, which is this. Okay, so I think that's it. This, yeah. Thank you. Do you have any question?
No.
Yeah. Okay. So let's call it a day. Thank you.
Oh, thank you.